Hello, my name is Fahad Alhomayani, and today I will present a poster entitled Oversampling Highly Imbalanced Indoor Positioning Data Using Deep Generative Models, which I co-authored with my PhD advisor, Dr. Mohammad Mahoor. The main motivation behind this contribution was that we found that often real-world indoor positioning data sets are imbalanced. And the problem is that training on imbalanced data may result in a model biased toward the majority classes. To address this problem, we propose the use of variational autoencoders and conditional variational autoencoders as data oversampling techniques on a highly imbalanced indoor fingerprinting dataset. The data used in this study was introduced by Aranda et al., and it is composed of Bluetooth low energy fingerprints. The data was collected from a 3-story building where each floor was comprised of two same-sized cubic structures or spaces joined by a hallway. The aim of the experimental setup is to assess the performance of variational autoencoders and conditional variational autoencoders by creating imbalanced versions of the training set and apply these models to generate synthetic fingerprints of the minority spaces so that all spaces are equally represented. In other words, an artificially balanced training set is created to train a downstream classifier that acted as a positioning model. Then we use the testing set to quantify the performance of the classifier according to metrics precision, recall, and F1 score, where the performance results are expressed as a relative change compared to the baseline, which is the performance of the classifier trained on the imbalanced version of the training set. This table presents the results of the experiments where each experiment corresponds to a different number of minority spaces ranging from 1 to 5 and compares them to those achieved by two state-of-the-art oversampling techniques, namely SMOTE and ADASYN. The results show that in all experiments using synthetic fingerprints generated by all oversampling techniques all lead to an improved F1 score for the minority spaces compared with classifiers trained on imbalanced datasets. Moreover, in all experiments, every oversampling technique also resulted in a better F1 score for the majority spaces and all spaces overall, which suggests that these oversampling techniques can enhance a classifier's overall learning ability, given that the improvements are not isolated to the minority spaces. As future work, we intend to undertake a more in-depth analysis of the results to answer questions such as why SMOTE and ADASYN generally outperform variational autoencoders and conditional variational autoencoders, and why does variational autoencoders generally produce better overall F1 scores than conditional variational autoencoders. Thank you very much for your attention, and I am happy to take any questions. Thank you.